I would now like to introduce our speaker. John has spoken with us on a number of occasions, not since COVID, he informed me, so it's been a while, which is good because I couldn't remember the last talk. I remembered he'd spoken, but I couldn't remember the talk. John is the York Research Chair in Space Exploration and the Director of Technologies for Exoplanetary Sciences, NSERC Create. He's a member of the Royal Society of Canada's College of New Scholars, Artists and Scientists, and the Canadian Aeronautics and Space Institute's 2022 McCurdy Award. He holds a BASc from U of T and a PhD from the University of Arizona in planetary science. He's been an author on nearly 80 peer-reviewed publications in planetary science and a member of 5 NASA and ESA-led space mission teams. His contributions, the contributions of his research group to robotic space exploration have been recognized with 16 NASA Group Achievement Awards. And his first popular science book, Daydreaming in the Solar System, co-authored with Jesse Rogerson, will be published by the MIT Press in October of this year. So watch for that. Please join me in welcoming John as he gives his talk entitled Our Celestial Rosetta Stone, Exploring Our Family of Planets. There you go. Join us in the processes across the cosmos.
Thank you so much for having me here tonight. I always love coming out to RASC Mississauga. It's my favorite group, and I don't say that to everybody. And the way that you know it's true is I've been here 4 times. This is my 4th time visiting this place. So, you know, I just love coming out Mississauga Road and taking, I guess, the QEW during rush hour. So tonight I'm doing something a little bit different than what I've done in the past. I want to talk about 2 different disciplines that are in dialogue with one. So you've got all of the amazing things that we've discovered with exoplanets and the amazing diversity of it, thousands and thousands of these things. But we don't know very much about any of them, really. We just have little tiny bits of data here and there. Then we've got our solar system. We go and we explore the planets and we learn an awful lot about them. And the question is, can we learn about our friends, the exoplanets, from what we have right here at home in our own solar system? So that's sort of the whole idea, the whole conceit behind this one. So let's see if we can go on to the next slide.
I saw it work before.
I know, I did too. Exciting.
You want me to sit there and push a button?
I hope you don't need that. It's upset with Zoom. Okay, now it's working. There we go.
I didn't do it.
So yeah, the exoplanets that are out there are weird. They're very, very strange places. So here's just 3 examples of some of the weirder ones. So we've got this planet, if I can get on the screen, there we go. So this is a disintegrating Mercury. It's a planet as big as Mercury, but it's very close to its star. So it's almost like a comet. And it's trailing this huge trail of debris and dust across its parent star. And here's one from just a couple of weeks ago. This is WASP 193b. This is a planet that has a density less than cotton candy. And you can see how an AI hallucinates given that prompt here. And over here, we've got another planet, and this one, you have temperatures that are so hot on this rocky planet that it actually rains liquid molten rock. What a crazy, crazy place. So there's some strange things out there, things that are a little bit different than what we have in our own solar system. But can we use what we know about planetary processes in general to understand what's going on out in the exoplanetary realm? So here I've got one of the TRAPPIST planets, I've got Mars, and then we've got our friend, the Rosetta Stone in the middle. Can we translate between these 2 things? You know, what can we do here? And it turns out we're already doing a little bit of this. And everyone in this room is actually, you don't even know it, but you're a bit familiar with this process. So let me show you what I mean by that. here we have a whole bunch of exoplanets. And I don't need to convince any of you, I don't think that these are planets. They're not pieces of fruit, they're not marbles or some kind of sports ball. These are planets, right? And how do we know that they're planets? That you might wonder that question. So if I take a look at two specific, I'm gonna pull out these two. So Earth, hopefully everyone's familiar with Earth.
Most.
And here we've got Kepler 62b. And we've got these lovely, lovely images of the two of them here. So with the Earth, this is an image taken from space of our home world. Kepler 62e, what's that? Is that an image taken by a telescope? But it turns out, no, it's this kind of thing. We've got an artist's opinion of what Kepler 62e looks like. That said, what you're seeing up here is probably pretty accurate. The continents may not be in the same places. The clouds may not be in the same places, but they probably are on this planet. They probably look something like this. And that's because our friend the artist here, what he's done is he has looked at our own solar system for examples of planets that are kind of like Kepler 62 and used that as examples. And so you're already seeing that kind of translation work going on when you see an artist's interpretation of what exoplanets look like. So let me show you real pictures of exoplanets. Here's the best one we've got. It's my personal favorite. Just get ready for this. So this is the HR 8799 system. And I've got a still over on one side here. So you can see 4 planets here, B, C, D, and E. They're orbiting around the parent star. And over here, we track the system over time. You can see the time moved out here. And you can actually watch the planets move around. Beautiful system. Lovely to see. But it's weird. There's a reason why we can see this particular system especially. And there's a couple of reasons for that. So first of all, these planets actually orbit quite a ways further from their star than we're used to in our solar system. So we have this unit called the astronomical unit. It's the distance between the Earth and the Sun. And there is a scale bar on these. So you can see 20 AU there, 20 AU there on the increased version. And as a result of that, these planets are a long, long ways away. So if you think of the furthest planet in our solar system, Neptune, it's something like 30 astronomical units away. But letter B up here is more than 100 away from its parent star. So we're cheating because we're taking the fireflies and we're moving them further away from the searchlight that is the star that we have to correct for, that we have to try to tamp down the light. The other thing that's going on here is that this system is really, really young. So the reason that that's important is because when solar systems are very young, everything in them is very hot. And so these planets actually are glowing of their own light. And the other thing is they're all way bigger than Jupiter. That helps too. So we have a really, really weird system. We're seeing it at just the right angle to get a great picture of it. But when it comes to solar systems like ours, we just can't get even pictures that are this good of those systems. So why don't we just go and visit these places? I am, somebody who studies space exploration. I love myself a good spaceship and a good mission. Let's just take a spaceship. Let's go and visit these other planets and take a good look. There's a problem. They're too darn far away. If you wanted to go to the nearest star system, to Proxima Centauri, and you wanted to do it using the best technology we have today, it would take something like 70,000 years to get there. And that's the Voyager probe. There are a few people who have an idea. The image you're seeing here is called breakthrough star shot, of taking a little tiny chip and putting it with big reflective sail, and then a Dr. Evil Death laser to send it on its way. And maybe it gets up to a fraction of the speed of light, and it gets to Alpha Centauri, Proxima Centauri within a few decades, and then sends another picture back in a few decades. This technology is still a long way from working. And unfortunately, I don't think anybody here is going to be around to see an image like that. So images that look like artist renderings of exoplanets, maybe not coming anytime soon, I'm sorry to tell you. So given that, can we actually still know these places? You know, they're just going to be points of light in the sky, who cares? Well, we can know them as worlds. We can understand how they work and how they function and the kinds of places they are. But we need to listen really carefully to the stars that they orbit. That's what we need to do to get the bits of information that hopefully then we can use our Rosetta Stone to translate using our own solar system. So let's take a look at some of the messages, some of the language of those stars when it comes to planets. So here we have a star, wonderful bluish star. And what we notice about stars that have planets, and when they're in the right orientation, is that they change their brightness from time to time. They'll be bright for a longish period, and then suddenly they'll dim. And they'll dim for a short period of time, hours, sometimes days, and they'll come back again. And then we'll have this regular pattern of up and down, and up and down, and up and down like this. So when this is happening with the star, we call this transit pattern. The reason we call it the transit pattern is because what's happening here is that the planets of this star are passing in front of the star itself. So what we're seeing is the shadow of that planet. It makes the star just a little bit dimmer, and that tells us not only that there's a planet in that system and how fast that planet is moving, so therefore how far from the star it is, but it also tells us how big the planet is. So that's a really useful thing. And this is something that we've gotten incredibly good at doing. So if you were to go ahead and imagine the first Canadian place, this is the Vivo Tower downtown Toronto, and you want to know how small a planet we can detect, how small a shadow we can find, current telescopes that we have in space can take a look at something that's as bright as the equivalent to the side of this building. And if you were to go into one office in this place and to take the window shade and move it down by 1 centimeter, our telescopes can detect that. So there's some very, very precise brightness calculations, or brightness measurements that are going on here. It's amazing what our technology can do, really. But that's what you need to find these kinds of rocky exoplanets, ones that are small, like the one that we live on here. Now, using that information, using the size of the planet, and we have other methods that give us the mass of the planet, how much stuff is in there, we can actually figure out things like what that planet is likely made of. So what I've got here, we have a sun-like star, that's the yellow in the background, and I'm imagining planets that are as massive as the Earth, and planets that are 5 times as massive as the Earth here. And what kind of shadow would they cast as they're made of different stuff? So if we were to make the planet out of pure iron, that's the smallest thing that you can imagine. You get the smallest shadow. As you build with different materials, you get all the way up to pure hydrogen. These ones are bigger, they're more puffed up. So by comparing the shadow and how much the planet weighs, we can actually tell whether we're dealing with a hydrogen planet, whether we're dealing with a carbon planet, an iron planet, all of these things. So it gives us the first little bit of information about what's going on. And that's not the only thing that we can learn from long distances. So the other thing that we can do, because we've got that really good precision at telling brightness differences, we can also take a look at different colors. So we can watch what happens here. And what's happening is the solid part of the planet, that's just black shadow. But around the rim of the planet, if it has an atmosphere, the light of the star shines through the atmosphere, and that atmosphere can either absorb or allow that light from the star through. And essentially what's happening is that shadow is getting bigger and smaller at different wavelengths, at different colors. So here you can see that the shadow gets bigger for sodium, that's the Na line, and bigger for potassium, the K line. So what's happening here is those are places where these elements are blocking the light. And so the atmosphere is itself casting a shadow. So this is really, really neat. This is probably where we're going to get the most exciting information from exoplanets in the future. Now, of course, being a good person here, I've been kind enough to show you all the simple cases that are uncomplicated and wonderful. In reality, these kinds of curves of this data is messy. And You know, sometimes you'll have, you know, different depths of the brightness change. Sometimes the brightness actually, you know, you'll see some of it as it goes around the backside of the planet too. And sometimes you get these perplexing, crazy things. So we need to figure out, you know, what this all means. And before I jump into that, I just wanted to take a minute to go through a thought exercise with you. So let's imagine that we have Mars, and we put Mars in another solar system as an exoplanet. Because I want to show just how little we actually know about exoplanets. I really want to hit this point home. So Mars is an exoplanet. Let's think about, you know, how much data we get. So let's say we're taking a look at that shadow and we're counting the times when the star is bright and when the star is dim. If you have Mars around another exoplanet and you do a really good job, you take images every 30 seconds, you get about 8 megabytes of data. Not a lot. Even if we do the spectroscopy thing, we take that light and we split it up into 2,000 different colors, just like James Webb does. Then you only end up with about 15 gigabytes of data. So that's what's going on the exoplanet side. Now, Mars is in our solar system. We know how to interrogate it from a planetary exploration perspective. If we take a look at it with a space telescope and we get the whole disk, so something like the Deep Space Climate Observatory, which looks at the Earth, now you're up to about 40 gigabytes. And if you have something like the HiRISE camera, which is in orbit around Mars, now you're up at about 20 exabytes. And, you know, this is a log-based graph. It's late, I know. It's, you know, trying to really tear this apart is hard. So I have a way of making this a little bit simpler. So it turns out, by the way, and I should mention that the numbers down here for the exoplanets, these are as big as it gets. For most exoplanets, it's actually less than that, just kilobytes of information. So I needed something to just sort of, you know, visually demonstrate what that looks like, the amount of data that we have on a typical exoplanet. And I thought, I've got something for that. So I have a little prop here. So basically, from a single exoplanet, most of the ones that are out there, everything we know about them can fit on one of these. And if you have people in the room under 30, ask for Jared. This historical artifact is right here. Yeah, this is a floppy diskette. It holds about 1.4 megabytes of data.
Quad.
I know.
Wow.
So, you know, this is the fancy kind. So I thought, you know, let's take a look at, you know, what kinds of stacks of floppy disks we need to hold the kind of data that I had in the last slide. So if you're talking about the exoplanet like Earth, you need about 6 of these. So they're about a dime thick. If you move up and do the spectroscopy thing, then you need a stack that's about 10,000 floppy disks thick, about as high as a blue whale. Now, if you come into the solar system and you're taking a look at the full disk of the planet, as you would from the Space Observatory, now you need about 30,000 of these, one on top of each other. And that's about equivalent to the height and center block of Parliament. But if you want to know a planet like we know Mars from orbit, with all of the richness that comes from that, well, then you need a stack of floppy disks that extends from the surface of the Earth all the way to Mars, just shy of 50 million kilometers of floppy disks.
Wow.
And that's a lot of them. So that just gives you a bit of an idea of what kind of a problem this is. We know our own planets so much better than we know the exoplanets. So let's think about translation. How do we use all that we know about our own solar system and transfer that over to give us an idea of what's happening on exoplanets? And so let me introduce you to the Rosetta Stone. I've been talking about this a little bit. Some of you may know some of the background on it, but I want to fill everyone in here. So I've zoomed in on this part over here. So these are hieroglyphics, ancient Egyptian writing. And it's very different from our writing. And in fact, when people start to study this not too long ago, a few hundred years back, the knowledge of what these pictographs meant was lost. So nobody knew what they meant. And there was wondering about what this could possibly have to do with anything, because you'd see it all over ancient monuments, and it was incomprehensible. But then, luckily, we unearthed this stele, so it's a stone, and what is written on this is the same thing in 3 different languages. So we've got the ancient Egyptian version up here, then there's a sort of a middle language, Slavonic down here, and then Greek. And of course, our colleagues over in archaeology are like, that's great, I know Greek. So because the same message is in all 3 languages, you can use the Greek to translate the Egyptian. And then suddenly, now we know what the ancient Egyptians were writing on their buildings, what it was that they were trying to say. We can do the same thing. We can take all of those weird curves and patterns that the stars tell us, and we can translate that language into planets by analogy with what we know of our own solar system. So that's the plan here. Let's see how good we are at doing this. So before we went out and explored the planets, we had a lot of information about one planet, the Earth. Let's see how that worked when we were thinking about Mars and we were thinking about Venus. So Mars, we saw the color change, and people thought, oh my, if the color's changing, it must be a vegetation change. Maybe that's what's happening on Mars. And then you saw the polar caps. Some folks like Schiaparelli thought that he saw canals. So we imagined this whole dying civilization, even though Schiaparelli was really just seeing his own retina because he hadn't set up his telescope properly. Then we have Venus. Venus is great. What makes Venus great is all we can see is clouds. So you could imagine anything you wanted underneath the clouds. So our friend Frank or Paul here imagines a whole dinosaur civilization with some very interesting transit options here and down here. Probably still faster than the TTC, to be honest. So we didn't do so great, comparing our Earth to what we see out in the solar system. But when we got out there, we were able to correct our assumptions. So here we have Mars on the top, and now we know that the color changes have to do with the way the dust moves. But we've also been able to go and ask scientific questions of Mars to better understand its story and how it's evolved, not just now, but in the past. And the same thing with Venus. We've got 2 images down here from the Venera landers. You can see that lovely yellowish hazy sky and platy ground there. But one of the really fascinating things about this is understanding how time works with it. Because both of these places look arid and desolate, but we know that both of these places actually had oceans in the past. So at one point or another, these were actually places that were kind of habitable, which is neat. All right, so now we have a few other planets. Let's see how we do when we go further out in the solar system. Let me show you another example here. So this is the discovery of the planet Pluto. These are copies of Clyde Tombaugh's plates from the 13-inch down at the Lowell Observatory, so 1930. And the way that you found planets back in those days is you took 2 images of the same piece of the sky and you looked for anything that moved, because if it moved between the images, it had to be in the solar system. So if you look at this little dot here, you'll find that in the next plate, it's in a different place. It's not there anymore. It's now over here. So from that, we know roughly how big Pluto is from the amount of light that was sent back to us. And we know how far away it is because we can see how quickly it moves. And yeah, everything else in these 2 images is a star, and it all stays in the same place. So that was wonderful. We knew where Pluto was, we knew roughly how big it was, making some assumptions as to how reflective it was. How did we do as we got better with our technology? Well, over time, we got slightly better versions of Pluto. So this is just that dot blown up like crazy. So that's really just one point. And then with Hubble, we got to the point where we could see that there was a little bit of darkening at the limb, which suggested maybe a bit of an atmosphere. And then we used some really sophisticated processing in 2003, and we got this kind of brightish, darkish kind of thing. By the way, we're starting to be able to do that kind of analysis with exoplanets, but that's probably about as far as we're going to get for the time being, unfortunately. But we were getting better, we wanted to know Pluto better. We decided we would send a spacecraft out to Pluto and see if our assumptions about how this place worked were correct. And we needed, in order to figure out what this spacecraft would look at, how it would record information and all of that, we needed some idea of what kind of processes went on Pluto and what it was made of and how it was set up. So we looked for good analogs, places that were like Pluto in our solar system, and we came across this place. So this is Triton. Triton is the largest moon of Neptune's, and it orbits in a way that, opposite the way that most things in the solar system orbit. So it's probably a captured object from out where Pluto lives. And so we looked at this place and we said, aha, we don't know what Pluto looks like, but it's probably something like this. Something with these kinds of materials, a lot of nitrogen, a lot of methane, maybe this kind of a color. And we saw an interesting process happening on Triton. We saw these vast geysers that were sending material skyward that would then get pushed along by the prevailing winds into dark streaks. So here's the artist's conception here. And if you look over here on Triton, you can see all of these sorts of little dark streaks. So we got ready, we sent out the spacecraft, we got our artist to make us a fictional image again, because we didn't actually have a picture of Pluto either. And you'll notice there's our friend the geysers up here. And this is New Horizons. It's about the size of a baby grand piano, by the way. So how do we do? Not too bad, as it turns out. Nitrogen, methane, both here. Orangey color, good. Gigantic heart, fantastic for public relations. So this is a big success story. You know, 4 years. But just like with Mars, just like with Venus, there's more to the story. So Pluto and Triton, they're not identical places, and that let us really refine our understanding of how planets work. As we get better at determining how planets work, that applies to our understanding of all planets everywhere, not just in our solar system, but across the galaxy and universe. So here's the big surprise. If you take a look at this image, so this is the final image looking back at Pluto after New Horizons have passed by. Look at the atmosphere here. All these nice little layers. So much scattering. It turns out there's a lot of dust in the atmosphere of Pluto. And that gives you such a richness of geological features. This was really unexpected. You ended up with an atmosphere around Pluto that was much thicker and much larger than anybody could have anticipated. The whole thing is essentially larger than the planet Earth. And because of that, you have different processes that are important than you had on Triton. When we take a look, we see all sorts of crazy things that you wouldn't have expected. Like there are sand dunes on Pluto. You can see the ridges if you look closely here, going back and forth. You know, we also get places where the terrain is just sculpted by the sun up here. And here's the edge of the heart. Here's where we get this cauldron of nitrogen bubbling up. And all of these water ice mountains that are just sort of floating like gigantic icebergs at the side of that bubbling nitrogen. By the way, it bubbles over millions of years. It's not too crazy. But still, it's a little bit interesting that we find out new things whenever we go and we check our assumptions. That's the great thing about science. If we knew what we were going to find, why go? So one thing I really love about this, by the way, is after all these discoveries, the scientists who were running the mission went out and they commissioned the new artists, the rendering right here. Note that the geysers are gone. So, they say that science is self-correcting, and here's some evidence that art is self-correcting too. So let's take what we've learned at our solar system and let's go back to the exoplanet realm. Let's see what we can figure out. And why don't we pick the biggest question there is when it comes to exoplanets, which is what is it that makes a planet habitable in the first place? Because we really care about that. That's life, water, all this good stuff. So the first thing, the most important thing is liquid water. So here's a lovely image. This is another artist's image by Chris Butler. And imagining, an astronaut very gingerly going into an alien ocean. Liquid water is important. The reason for that is that life depends on chemical reactions. And those chemical reactions have to happen somewhere. If they happen in a vacuum, if they happen in gas, it's too rarefied, and the molecules just don't run into each other enough for anything much to happen. So you need something like a liquid, and water is pretty much the perfect liquid for this to happen. Liquid water on the surface of the planet is really good. We know that you can also get liquid water inside a planet. So here is Enceladus, technically a moon of Saturn's. And we know that there's a liquid water ocean inside this place because you can see it jetting out into space. It's really obvious, which is nice for us. But we don't know what's going on inside there. That's where the action's happening. That's where the interesting stuff is going on. When you think about all of the icy moons of the solar system, there's more habitable volume in those than on the Earth by a long shot. And who knows what could be in there, maybe even that. So this is a lovely image actually from the forthcoming book. It's a little preview there for everyone. Imagining a sub here being assailed by something with tentacles.
Ooh.
Exploring this from a solar system perspective is a great idea. I personally would love to see before I die what's inside of one of these places. I'm very curious, I have to tell you. And if we do find anything that is alive in these places, then that tells us something probably about our own origins as well. On the Earth, perhaps life began on the surface, or maybe it began sort of in deep sea vents. And if you go to a place like this, there's no water on the surface, so only one of those hypotheses actually works. That said, for exoplanets, this type of environment is a dead end. And the reason it's a dead end is because we just can't observe this stuff from light years away. We can't even observe this stuff from the Earth. We have to go out to Enceladus, we have to break through the ice, go down into that water and see what's there. And we just can't do that in another solar system. So even though this is a great place for life to be, because we can't actually interrogate it, we're going to ignore it. And we're going to look for atmospheres. It's the same thing with those of you who know the Drake equation, for instance. The definition of an intelligent species is one that's capable of building a radio telescope. And the reason it's that is because you can't talk to a species without a radio telescope. So atmospheres is what we need. This is a lovely one for Titan. Gives you an idea of the types of colors and the types of things that are going on in these places. And what we want with this atmosphere is to be able to find the chemicals that make up life. So we want to find water. We want to find other interesting things. And we've started now to find atmospheres in other solar systems with water. So here's a lovely one here. This is WASP 39b. Spread out all of the colors and you get this little curve. And it turns out there are bumps and wiggles associated with good old H2O. Hooray. Of course, WASP 39b is a hot Saturn and it's 800 degrees Celsius, but it's a start. The hope is that we find more planets that have temperatures that make sense to us that also have water in their atmospheres. And that brings me to the second point. You need a place that's not too hot and that's not too cold. So this is, again, some examples from our own solar system. We have Io, the most volcanically active body in the solar system. And then we have some frozen plains on Mars. So you need something that's sort of, in the Goldilocks zone. And the reason that temperature matters comes again back to the chemistry of life and how that works. So if it's too cold, then the dance between molecules is very slow. And it takes too much time for those molecules to come together into anything that's alive. This is the problem we have on Titan, which is a big moon of Saturn, has lots of wonderful hydrocarbons, but it's also 200 degrees below zero. So the dance is too slow. At the same time, if it's too hot, then the processes that take apart the chemistry of life happen quicker than the processes that build it up. And if you want to try this out, next time you have a bonfire, go and stand in it. And if you heal faster than you cook, then it's the right temperature for life. But it's unfortunately, you will burn up first. So that's an example of it being too hot for life. And because carbon is pretty much the universal compound out of which you build things, this is probably the same in other solar systems than it is here. So my apologies to the Silicon Life people, probably not. So using these two criteria, we can create this idea of the habitable or Goldilocks zone. And you can see here for a star like our sun, and here's our solar system in there. Earth, habitable, correct. Mars, not so much. Venus, also not so much. But it's a little bit more complicated than that. The reason being that we can imagine atmospheres that Mars or Venus could have that would make them habitable. So it's actually probably a little wider. And as we dial up the sun, as we make the star brighter, that habitable zone should move out. As we dim it down and make the star dimmer, that habitable zone should move in. And it can move in a lot because the smallest stars are, of course, more populous. There's more of those red dwarfs than there are sun-like stars. And we can take a look at an example of this using everybody's favorite exoplanetary solar system. I'm talking, of course, about TRAPPIST-1. So TRAPPIST-1 is around a red dwarf star, and we have found so many planets here. Like we have to go all the way out to H to get here. This is definitely, seating on a wide body aircraft to get all of your planets in. And the nice thing about this one is that you've got 3 planets that are in that zone where we think it's not too hot and it's not too cold. So you've got, E, F, and G right there. And these are all big planets. These are Earth-sized planets. They're rocky, and they're really fascinating places. But this system is tiny. If I show it on the same scale as our own solar system, you have to fit it all the way down in here. So it's actually well inside the orbit of Mercury because the star is so dim. But man, being on one of those planets and looking up the night sky would be incredible. You'd see all these other planets, and imagine if they actually were habitable. Imagine if you looked up at those places and you could see, clouds, and you could see rivers and lakes and continents and stuff. That would just be amazing. And I'd love to ride this train. Now, we've got this challenge, of course, that even when you're in the habitable zone, it's not a guarantee that you're going to be inhabited. So we are looking for planetary atmospheres for the TRAPPIST planets. We're doing this with Webb. We haven't found them yet. So that's a bit worrying. We're not completely finished. We haven't confirmed that there's no atmospheres, but they're proving to be harder to find than you might imagine. And that's bad news. We have a good example in our own solar system for how bad the news can be. And that's the moon. The moon sits right in the middle of our habitable zone, and it is not a very habitable place at all. I personally do not want to go out on the moon without a spacesuit. That would be bad. So if these planets don't have atmospheres either, then they might look more like the moon than they look like the Earth, which is unfortunate. So some astronomers think that really what we should be doing is looking for places that are unlike any that we see in our solar system. And they have their money on these guys. So this is a super Earth. So super Earths are really neat places. They're somewhere in size between the Earth and Uranus and Neptune. So somewhere in there, we don't have an example of them in our solar system. This one here is TOI 715b. And because we don't have an example in our solar system, they drive artists crazy. So this one here, I love the green. I just adore the green. The red blotches, wonderful. This one's a little more terrestrial. But I've also seen this exact same exoplanet represented like this. So this is more gas giant. My personal favorite is this one where the artist decided, I don't know, so I'm not going to draw anything. And then there's ones like this that I just, they're beautiful to look at. The reason that super Earths are interesting is that they should have super thick atmospheres that really protect what's happening down, at the bottom of those atmospheres. And many of them are likely water worlds with a lot of liquid down there. So we should get that signal from the liquid in their atmospheres, and we should be able to see other compounds related to life. So these are really, really interesting places. But what it kind of tells us is, unfortunately, we can't go and visit one of these places to understand. We have to know more about planetary processes in general, which means we need to go back to our own solar system and ask deeper questions, because we can go and look at things here that we can't look at elsewhere. We can take a look at meteorites, for instance, which tell us about the materials out of which the planets formed. We can go to each one of the representatives we have out there and take a look at its processes and move it backwards and forwards in time that way. So that's a really helpful thing to do. Now, I mentioned at the start of the talk that these are two disciplines that are in dialogue. So we can learn about exoplanets by exploring our own solar system, but we can also learn about our own solar system by exploring exoplanets, in the sense that we can get a huge census of all the different things that are possible out there. So you can run this actually completely in reverse. And one of the things that we've already done with this that's really helpful is to tell us a little bit about the beginnings and the endings of our own solar system. So if we start with the beginnings here, here's a lovely image of the Orion Nebula. I probably don't need to tell anybody in this room what this is, but this is the Orion Nebula, one of the brightest in the sky. And we can zoom in on this thing. When we do that, what we find is there's a whole bunch of really interesting features. So these are all just baby solar systems, just born and putting off a lot of energy, just starting to contract, just starting to form planets. And this tells us an awful lot about where we came from, the origins of the solar system. So that's helpful to our understanding of our own place in space. We also know something about the ends of our solar system, what's going to happen when the sun starts to run out of fuel. So this, of course, is the Ring Nebula. This is I believe this is a web image of it. And you can see the star has sloughed off all of its outer material. It's baked all of its planets, unfortunately. And now it's just a little white cinder in the middle. So this tells us sort of about where we're going. Over time, as we get to know planetary processes better, as we get a full census of what's in the galaxy, we're going to be able to do finer grades of this. And at some point, we might be able to tell, how we get from a planet like the Earth to a planet like Venus. Make sure that we don't become that. Where are those tipping points, in things like climate? How do we make sure that we keep the Earth a habitable place? So you have to do this dialogue, and you have to go out and you have to explore in our own solar system and still use telescopes further out. And this is a great time for it. This is an exciting time where we're discovering exoplanets. We're still learning so much about our own planets, and there's a lot left to be learned about what's going on right here, Phil. So this is a painting that Carl Sagan had commissioned of the inside of the atmosphere of Jupiter, and that's actually Carl there. You can see this back in shadow. I just love the man's words sometimes. How lucky we are to live in this time, the first moment in human history, when we're in fact visiting other worlds. We're actually going out and seeing these places. And this wonderful painting that he has here has some interesting things hidden in it. There's lovely Easter eggs. Take a look at these things. These are all hiding in there. So he imagined a whole ecosystem that maybe you had, simple materials coming up that could be eaten. So those are his sinkers down here. And maybe you had big bags of gas that were consuming those, maybe kilometers across. So that's the floaters. And then maybe something hunts the floaters, which would be hunters, of course. Carl wasn't necessarily the most creative. But imagine this whole ecosystem is really interesting. And it was fun to see this come up again when people were talking about phosphine in the atmosphere of Venus a couple of years ago. What could be happening again in cloud layers? Let's take a look again. That was a wonderful artist reference. Let's take a look at the real thing. So here is Jupiter, and here is our highest resolution image of Jupiter. So what you're seeing here, this lovely mixture of gases, you can sort of see it along here. You're getting down to about 4 kilometers per pixel. And if you take a look at the pinpricks there, those are all really gigantic thunderheads. They're like this, 50 kilometers in size, enormous convective systems. And it makes you think, when you take a look at an image like that, if the pixel size is 4 kilometers on a side, then none of these things are visible. I can't tell you with 100% certainty that there are no hunters, sinkers, and floaters on Jupiter. So I think that is just absolutely fascinating. I love that we live in a universe where there are still big questions like that we can ask and that we can think about. So I wanted to leave you with just one more thought. Got a lovely image here, and it makes me wonder if there are things on Jupiter that we can't explain yet, don't understand. What about when you get out to the exoplanetary realm? What could be waiting sort of out there in those really deep waters of the galaxy? What's hiding in each and every little sunbeam? And you might think back to that image I showed you of the exoplanets going around and around of that star. This thing here, this is, of course, not actually an exoplanet. This is an image of the Earth. So there's a lot of stuff hiding in this image. Really, I mean, again, to quote Carl, this is on that one little pale blue dot. That's where, everybody you've ever heard of, every story, every dictator, every, great work of engineering, everything, it's all there. All the life that we know of in the universe is on that one little dot. So just think about the fact that there are hundreds of billions more of those out there in the galaxy. And what might be living or hiding, or questions to answer, puzzles. So with that, I will be happy to take any questions you may have.
All right.
Let's kick it off.
First question. You mentioned the Drake equation, and you mentioned that we figure, well, at least for us to be able to detect civilizations, they need radio telescopes. So, does it make sense to look at? It doesn't make sense, I think, unless you tell me otherwise, to look at water-based planets for radio telescopes, because you can't have any. I can't think of how a civilization could develop electronics with water. You need land. Yeah?
Well, I mean, there's got to be land down there somewhere, you would imagine.
Right, but so you fill a bubble with air and so it doesn't short circuit? That's what I'm getting at.
Oh,
Yeah.
Yeah, I don't know. I have to say, I can't imagine really what that civilization would be like and how they get to electronics. I don't know that it's impossible, but you're worried about worlds that are completely water.
Yeah.
Yeah. I think that probably takes me a little too far past my expertise.
Okay, yeah, agreed. Okay.
Yes.
These cotton candy planets, these worlds, they're so puffy, and the force of gravity's got to be barely holding on to the other parts of their atmosphere. So, are we looking at planets that are only going to be there for a little while? Where we catch them a good time and they're just going to evaporate?
It could be, or there are planets that are cooling and they'll get smaller over time as well. They're just puffed up because they're warm, for instance. And, we're looking at them in wavelengths where they cast a really big shadow, so they appear to be, very, very big.
So it could be like in a young solar system, and we're just observe all that heat is from their heat of Benson.
Exactly. So that could be one of the situations in which you get a world that looks like that. And the press loves, anything, the greatest, the biggest, the smallest, the least dense. And if you have a good analogy, that works. There's lots of tasty places in the solar system.
Well, I like the colors you use for the cotton candy planet.
I can't take credit for that. That's old Dolly. Goes great with the creme brulee on site.
Yeah, some examples where you said we got lucky, like one was orbiting, like there were huge planets and they were hot and glowing, and the other method was the transit method. Like, do you have any sense of like those sound like the easy ones for us to see? Like, what percentage are there that are?
Yeah, with the transit method, you need to be edge on, right? Or else the planets don't come across the star at all. Unless again they're warm, and then you sort of see this sort of waviness as opposed to like a big shadow. There are people who have done that kind of analysis, thinking about if everything is orientated randomly, how many star systems should we actually be able to see? And that's where the estimate that there are more planets than stars in our galaxy comes from. And when you back up what should be observable, you actually have a lot of solar systems that we can't see at all. And there are other methods that can do a little bit better. So I didn't talk about the radial velocity method, for instance, which is where you're looking at a planet that pulls a star around. In that case, you can see those over a broader range of angles. So that gives us a little bit more information about how that changes as the orientation of the sky changes. Yes?
Find oxygen around the planet. Oxygen is such a reactive gas that binds the whole. So if there is oxygen in the exoplanet's atmosphere, must be something producing the oxygen. If there was just the oxygen, it would have combined with silicon. But you can have the technology now to detect oxygen around an exoplanet and have we detect oxygen around an exoplanet.
We do. I think that one has been seen, but I think the problem is context. That it depends on what is the mixture other than oxygen in the atmosphere, because there's some atmospheres where free oxygen actually would be expected. It wouldn't have anything to do with life. So to give you an example with the solar system, where I'm a little bit more familiar with the chemistry, if you look at a compound like methane, for instance. So methane in the Earth's atmosphere comes mostly from life. On Mars, we see a little bit of methane, and we're very excited because we don't know what's going on with that. But when you go further out to a place like Titan, Titan's atmosphere is 5% methane. And because of the mix of gases and the temperature out there, we don't think that means anything. That's just the kind of compound that should exist naturally in that environment. So I don't believe we have found oxygen in a place where it's going to make us excited yet. But yeah, exactly what constitutes a biosignature is actually a really hard problem. Yes.
You mentioned the extended atmosphere of Pluto that was detected from the far side. Is that due to outgassing? It must be losing that atmosphere. No, if it's that far away.
So it actually doesn't lose all that much of it, as it turns out, because the atmosphere is also very cold. So what you have happening, the really weird thing about Pluto is that it's the dust that matters more than the gas for all of the energy that's being received and that's being transferred around. So the presence of that dust causes the gas to be found a little bit higher, but it goes through these huge swings as well. Like Pluto has an eccentric orbit, so it changes a lot of its distance to the sun. And right now we're in a period where the atmosphere is puffed up. Within a few decades, Pluto will be back in a deep freeze, and we'll basically not have any detectable atmosphere at all. So there's these short periods of time when the atmosphere is alive, and then most of the time, it's just an icy rock. Yes?
Where do you think life is in the cosmos?
Yeah, that's a good question. I personally, of all of the theories that I've seen, I kind of like the idea of what's called the rare earth hypothesis. So the idea that simple life might actually be more common than we imagine, but complicated life is probably harder to find. Yeah, and there's a lot of people working on this, people much smarter than me, who have invested their careers in trying to chip away at that problem, and it is a difficult one to get a handle on. We keep finding, even on the Earth, we keep finding in places where we think there's no life, something that's managed to hang on and eke out an existence there. So really, we don't understand life on the Earth yet, and we can actually interact with that. So, out in the cosmos, it's a hard problem. Yes.
A number of years ago, I saw a presentation by a physicist, I don't remember his name, and he said that they were working on detecting, for planets that don't line up with the planet exactly, the phase that they're lit by the star itself and actually being able to do some figure things out from that. Have you heard any progress on that at all, or?
Yeah, there has been some mapping done of exoplanets. Generally, they're the bigger ones, like the gas giants.
Yeah.
And the level of mapping that we're able to do is like the image of Pluto that I showed you.
Okay.
So, this place is a bit lighter than that place, and that place is a bit darker. It's been used to look at winds often because we look for the hot spot on the gas giant. And if it's actually tipped to one side, and that tells us that the winds are taking the hot gas and pushing them in one direction or another. There is a Canadian who does a lot of really good work on this, Nick Cowan's his name, from McGill. So it's exciting work, and it's amazing what they can pull out. But it's not like the artists in it.
Not much happening yet.
Well, it gets better every year. Which is nice.
Will the upcoming 30-meter-ish telescopes provide more better quality images of any of this, or will they not be as appropriate for that kind of search?
So it's not so much detail because the resolving power is still going to be very hard, but they'll give us more accuracy, like that measurement of brightness, for instance. Maybe you can go beyond, one window shade down 1 centimeter, maybe we'll get to one window shade down 1 millimeter type of accuracy for things like exoplanets. But it's always difficult when you have to look through the Earth's atmosphere, and it's just a challenge. So there's a reason why we actually go out and explore the solar system as opposed to just building gigantic telescopes on planet Earth. We lose with the resolution and have trouble with things like this. Yes.
Referred to Enceladus as technically Saturn, I caught that. And I was wondering why you said it's technical.
Well, Enceladus is more moony than other places. Like if I think of, say, another moon of Saturn, it's Titan. Titan is a moon of Saturn just because it's it's in orbit around Saturn, so that counts. But it has a higher pressure at its surface than the Earth does. It's bigger than the planet Mercury. So if it wasn't, chained to Saturn, by all counts, it would be a planet. And, I just think of all of these places that have some inherent interest in them as sort of worlds in their own right. So I didn't mean to, to give the impression that I'm disrespecting the IAU or anything like that. But I don't know, I just find these places interesting, right? These, even though they are movies. Yes.
I'm going to ask a question that's not really your area, but I wanted to ask it anyway. So when the telescopes look into the past and they see galaxies that are 10 billion light years away, if we could see them right now, what would be they? Would they all just be big black holes? Would they have just disappeared?
Well, a lot of them probably look like what our Milky Way looks like now, because they've been evolving along similar paths to what we've been evolving. You can imagine the opposite question, right? Like if somebody was out there looking at us, 10 billion years in their past, they would probably see something similar, that the universe is fairly similar from all angles in all directions. So yeah, that's our best guess, is that, what we see locally is probably what these places look like now. And that's why we can assume that when we see 10 billion light years out, 10 billion years in the past, we're seeing something that is equivalent to our own past.
And is our galaxy that old?
Oh, that's a tough question for me. I'm just a simple country planetary scientist. But yeah, I don't know how one counts the age of galaxies. Of course, always merging. So, either or, I'll start here and then go to the list. So.
Okay, so you were talking about how the data from Mars is super useful. Exoplanet. Are there any space programs in the local solar system people like you are looking for because it's going to help people like exoplanet?
Oh Oh, yeah, like you see a lot more exploration of Venus now. And one of the strong desires is to understand what makes Venus tick. Not just because it's such a similar planet to Earth, but it's in a similar part of the solar system. So if you saw a planet where Venus was located with a strong signal of an atmosphere in another solar system, you guess that that's probably a good place, to find some habitability. We can't really distinguish easily between these places. So if we can find out more about Venus's history, how it was put together, then we can get a better idea of how long these places remain habitable. And if we see places like them in other solar systems, probability that they're habitable now or habitable. So, we do ask those kinds of questions, and we do try to use the excitement of exoplanetary astronomy and discovery to motivate understanding more about planetary processes in general, which help us everywhere.
It looks like you're developing a taxonomy here, and I'm trying to draw a relationship between what you're doing and what biologists have done. So nowadays you can pick away at taxonomy by looking at DNA. Before that, there were people like Linnaeus who figured out speciation. There's the concept of evolution and change over time that sort of helped inform that. You have fewer organisms to pick at. Well, actually, you don't have fewer, they're just further away.
Yeah.
Harder to see. Is there a conceptual framework akin to evolution or Linnaeus's sort of approach to categorization that informs the sort of work that we do?
It's a good question. And it's interesting because, of course, astronomy tends to live with physics, and physics is not, generally speaking, a taxonomic science. It tries to stay away from that as much as possible. Although some of the people working in planetary, they come from geology and biology, which are taxonomic sciences. So there's tension.
Table was created long before anyone had a sense of what the underlying structure was, which now we think is physics, but it wasn't in its original categorization.
Oh yeah, and certainly when we're looking out into the universe, we're trying to figure out, how do you classify and categorize these worlds. But I think part of it is because it's physicists who are doing it who have that mentality that they're imagining that there's a continuum, and they're trying to find things on the continuum and what are the edges of the continuum out there. So you see less, I think, of that kind of broad categorization. We still do argue from time to time, moon versus planet, planet versus dwarf planet kind of thing. But I think most scientists who study planets sort of think of these things more as a continuum. I haven't seen any big fights over, what's a giant planet and what's a brown dwarf, for instance. So I'm sure that they exist somewhere in the public.
As a scientist, how much do you look forward to a manned mission, assuming we ever get to Mars? And would you expect more to be learned from it, or are you totally in favor of robotic only?
Well, I do a lot of robotic missions myself, so of course from a selfish perspective.
I have
love
both perspectives, okay?
Exactly.
Okay.
Yeah, and I can tell you, we do have these arguments at the top. So there's a difference, right? When you're going out there with astronauts, then you get people who have situational awareness who can bring sort of that human perspective to the place that they're going. That can be handy. It's something you don't quite get with the robots. You don't quite get that presence. You don't quite get that story. And you can see, especially amongst the public, that the idea of astronauts going out, visiting these places is a stronger draw because it actually includes these places into human culture in a much deeper way than you get with just robotic exploration. So, I kind of think the two of them sit side by side. If we decided we're never doing humans again, robots are clearly a better way. I have a feeling that exploration program might be at risk of petering out. So you need both components, both sides of it, and they bring something different to the table. But human exploration, wow, it's expensive.
We have the same kind of.
Yes.
Okay, so this talk was on exoplanets and what we can learn about them. And I know you've got a popular science book coming out, which is excellent. Yeah. Ta-da! Yes.
We actually have the illustrator in the audience.
Okay, excellent. Well, tell them to get the front cover up on Indigo because
I know.
to
I
come.
know.
Yeah, exactly.
It's the only one of all of the sites out there. So Walmart and Target, they both have it, the actual cover, but I don't know why Indigo.
That's the cover?
That's the cover.
Well, okay.
It's a beautiful cover.
Yes.
a beautiful.
But I know that you've been involved in a lot of NASA and ESA missions. What is your current area of focus? Is it exoplanets, or are you working on any robotic missions or what?
Yeah, many of my students work with the Curiosity rover. That's sort of our bread and butter. So we're part of the science and operations team for that decides what the robot does on any particular day. And I've got a member of my lab also in the audience who does some of that work too. So that's sort of our day to day. We also look at scientific problems across the solar system, and we collaborate with others to do some of these problems that exist in the exoplanetary realm as well. So one of my previous PhD students actually studied and wrote a number of really fantastic papers on the rock rain, the molten rock rain. So that was a fun exploration that we had.
Thank you.
I'll start.
Sure.
Go ahead, sir.
That image that you showed, I guess, is a series of images showing the rotation around that goes over a 7-year time span. Right?
Yes.
What frequency was that? Like, was that radio? Was that infrared? What would generate that?
Yeah, I believe that one is near infrared, but I would need to double check. It is a ground-based telescope, and they were able to blot out the light of the star by actually taking the telescope and rotating it on its own axis. So often with space telescopes in particular, we'll put out what's called a coronagraph out, and we'll actually block the light from the star. But this telescope, had this added capability that it could rotate on its own axis, and so you could actually compare different angles. Yeah, do that. I think it's in the infrared.
Are radio telescopes used at all for a planetary, like distant planetary detection?
I haven't seen that so much. I do know that some of the early detections around pulsars using the pulsar timing technique is done with radio. I don't know how much of that happens these days. Really, most things around pulsars are not very interesting places, right? Because they've had this violent event in their past, which is bad for planets. So I think people are more interested in, especially infrared wavelengths, optical wavelengths, things like that. Less so big.
The reason I ask is that I know that, but planets in our own solar system, you can even DIY telescopes that can listen. I'm wondering if that applies to.
There has been talk of looking at aurora and some of the, if you have like a radiation torus like Jupiter has, essentially a synchrotron, that you could do some of that kind of work. But I will admit, it doesn't mean that there's not papers out there on this, but I've not seen any of them myself.
Reading a lot about all those hot Jupiters that are down from the stars. But in our solar system, gas giants are much further away from the star. Is it thinking now that the other star systems we're finding are more typical, that Jupiter towards the star, and would therefore wipe out all the small rocky worlds near the star? Might that mean it's less likely there's planets that have life up there because they're destroyed?
There's definitely a lot of stellar systems where even in our own solar system, the giant planets migrated in the past. We have evidence of that when we look at the asteroid belt. The great thing about that is you had Jupiter and Saturn that could interfere with each other and try to kick each other out of the solar system. The Titans just fought and then left everyone else alone, essentially. But But there are lots of solar system configurations where you do get those Jupiters that can move in. I wouldn't say that it's the majority of systems, and we're always very cautious about that one because hot Jupiters are the easiest thing to find when it comes to looking for exoplanets. Like they're the ones that we found first. I remember when I was in grad school, 2003, hot Jupiters were all that we were finding. And people were tearing their heads out trying to figure out, why is the sky full of giant planets really close to stars? So there's a bias in there that we have to be cognizant of. But there seem to be plenty of stellar systems that don't have a big giant planet close to the star. So I don't know the fraction of the two types, but I don't think it's as common and as disastrous as it appeared at least 20 years ago. Yes.
What is the general scientist's impression and concern about the heating of the earth over the next 50 years or so? What do the scientists think? Are they blasé about it or what?
I wouldn't say they're blasé about it. So there's the IPCC, the International, I believe it's Panel on Climate Change, that is part of the UN. So that's a big consensus of a couple thousand scientists. And they publish reports every few years of what the models are suggesting for the rise in temperatures over the rest of this century and a little bit beyond as well. And I think they've been trying to raise the alarm for some time. So I wouldn't say that they're, certainly the climate scientists are not blasé about it at all. They're very worried about what might be coming. We can't end on that.
What a downer.
So are you, I am, my undergrad degree is in geology, so the pictures that come, I did service hydrology, so the pictures that come from curiosity, I just look at that and go, it's just fascinating, because I've seen that before.
A conglomerate.
Yeah, and whatever. So when are we gonna get the samples that come back? I know I believe in the samples, but it'd be just amazing to just put those under a petrographic microscope and see what the chemistry is.
Absolutely, absolutely. And Mars sample return is one of these things that is always 15 years in the future, no matter what time you look at it.
Oh, kind of like nuclear fusion.
A little bit. It's interesting, I think, and one of the things that's really getting a lot of play in the media now is this idea that maybe NASA did not allocate a sufficient number of resources to MSR, that it's more expensive and harder than they anticipated. So that seems like it's slowing down the process. For a while there, it was almost 15 years in the future, and then we had this plan in the mid-2010s to do MSR in the 2020s. We had Perseverance, which was the first step of that. And the plan was, let's bring everything back at the end of the 2020s. Worst case, 2033, because 2033 is the best opportunity to bring things back from Mars. Maybe we'll even send astronauts then, that was the hope. Now it's looking more like 40, unfortunately, because of the constrained fiscal environment, mostly in the US. And it's a challenge. It's not an easy thing to do, even without human beings in the mix. You're talking about, you've got Perseverance that's there investigating samples, making sure that they're well documented, sticking them in containers. Then you've got to send another spacecraft to go and get the samples from Perseverance. That spacecraft has to bring its own rocket, send them into orbit. And then you do this little dance in orbit with my personal favorite spacecraft, the orbiting sphere. It is a soccer ball sized piece of aluminum, and that is it. The idea behind that is you want to break the chain. You want to be able to not carry any of the stuff that's on Mars with you to the Earth. And then another spacecraft comes and collects the orbiting sphere, brings that back to the Earth. So this chain of events is just absolutely incredible. And you think about the amount of moon rocks that came back from the Apollo missions, hundreds of pounds. Whereas for Mars, if we get 200 grams of material, we'll be doing well. you know, through this whole sequence, which is probably going to cost somewhere between 10 and $20 billion, which, as I point out to my astronomer friends, is only 2 webs. So, yeah. But yeah, that would be fantastic. And the thing I love about planetary science, and we're slowly converting our astronomer friends to the dark side here, is you've got the convergence of geology and atmospheric science. And I took a hydrology course in grad school too, and it was fantastic. Along with the astronomy, along with you know, the engineering as well that goes with it. And I just love the interplay of all of those things. Yes.
One more, okay. That slide you had with the tentacle creature, Enceladus was it, or Europa?
Yeah, that one's technically Europa in the book.
Europa, okay. So, if you were to put a percentage chance on it of 0 to 100%, chance there's multicellular life somewhere in our solar system, on one of these oceans, less than 1%?
Well, I can't say they don't have a radio telescope.
Yeah,
Yeah, that's
because of the water.
exactly.
Yeah.
Yeah, it's a question that I don't even know how to attack. I love to show slides like that because it just reminds us of the, you know, the places off the edges of the map that, you know, draw us, that make us want to explore, to go and make us. Exactly.
Yeah.
You know, to make the unknown known. And I like my questions unanswerable like that a little bit. So my apologies, I'm rapidly talking around the percentages.
It's between 0 and 100 though.
I'd say so.
Yeah. Okay.
50% probability.
Yeah.